Alright, so in this video we are going to go over section 6.1, angles and their measure. So in these few chapters we're going to discuss most or pretty much all related to trigonometry. So let's define real quick what trigonometric functions are. And so trigonometric functions are functions that are related to angles, and then they're used to relate the angles of a triangle to the length of the sides of a triangle. In the meantime, well, we're going to refer to actual points on a circle, and then later on we're going to make a relation to those aforementioned triangles, right? And so we need a system we need a specific system to make measurements about angles and all that. So what we're going to do in this case is, well, so we need to define basic ideas from geometry and then bring them to our vocabulary here in trigonometry. All right, so in this part of the section we are going to discuss converting between decimals and degrees, minutes, and seconds. But we need a little bit of some background to put that together well. So let's define what a ray is. So a ray is a portion of a line that starts at a point V on the line and extends indefinitely in one direction. So the starting point of V of a ray, it's called its vertex. So first of all, let's make a distinction between a ray and a segment. So for example, this right here is a segment that goes from A to B. All right, as opposed to a ray that goes from the starting point and it goes indefinitely. It goes indefinitely all the way to infinity. So this is V, the vertex, and this is called a ray. All right. Now, if the rays are drawn with a common vertex, they form an angle. What do we mean by that? So let's say from this ray, we do the following, and we do this. This space form right here, it's going to be called the angle. For example, let me do a couple of examples of angles. That's one. Let me draw these three. Okay, so we are going to call this the initial side, and terminal side. And the space that is formed in between the two rays is called the angle. That's the angle. That's the space. All right. And well, we use different letters to denote angles. We use the letters alpha, beta, gamma, theta. That's the one that we're going to use the most in this class, and phi. Okay. So for example, we can call this simply alpha. That's fine. And angles can go in different directions. For example, this angle can go in, well, in this case, this is a counterclockwise rotation because it goes against the clock, in the direction against the clock. That's a positive angle. And in this, but we also can have negative angles. And in this case, they go clockwise. Let's call this beta. And this is still initial. And this is terminal. This is also going to be initial. This is going to be terminal. Let's use a different letter. So for example, we can do, instead of going just here, we can do the entire rotation and then reach the same angle again and do multiple rotations. That's why we call this function, these trigonometric functions, we're going to call them periodic, because at one point we do one rotation and another rotation, many rotations, and we arrive to the same point. Okay, well, let's call this gamma. All right, call that gamma. Natural angle gamma. All right. So, an angle is said to be in a standard position if its vertex is at the origin of a rectangular coordinate system and its initial side coincides with the positive x-axis. The terminal side will lie in either a quadrant, in which case we say that theta lies in that quadrant, or on the x-axis or the y-axis. Okay, so rather, if, yeah, this is very, very important, if these quadrantal angles. What do we mean by quadrantal angles? Well, let me just give a couple of examples. So that's one right here. That's another one, and that's our angle theta. Whatever that is, doesn't matter. All we need to know is that this lies in the second quadrant. And then we have another example, another angle. And in this case, again, keep in mind that we can go in the negative direction. That's clockwise. This is in the fourth quadrant. And last but not least, there's another example of a quadrantal angle. So in this case, an angle that lies exactly on one of the axes, either the x-axis or the y-axis. For example, this one, which is 270 degrees. This is one of those quadrantal angles. Another example of a quadrantal angle, if this is the 90-degree angle, let me just draw it real quick. In the dashed line, it will be all the way here. That's another quadrantal angle. Okay, so how do we measure angles? So what's the idea? The idea is that there are 360 degrees that represent a complete rotation from the initial side to, again, coming back to the initial side. So if in this case we divide this in exactly 360 degrees, well, 1 degree is equivalent to 1 over 360 of a complete revolution. Special definitions, or a special vocabulary that you may have heard before: right angle. We know what a right angle is, which in this case measures 90 degrees or 1/4 of a revolution. On the other hand, we have another special angle, which is the straight angle, which is an angle that measures 180 degrees or 1/2 of the rotation. All right, so let's approximate. Let's do a couple of examples and approximate the location of these following angles. All right, so 1/4 of a rotation is actually 90 degrees, and half of a rotation is 180 degrees. If we will, let's write this down over here. 90 degrees, 108. Well, let me actually skip this one for a second. We will do something about this one because that's going to work out differently. Okay, so let's see. So 135 degrees is definitely an angle that lies between these two. Well, let's just approximate this its position. No need to be very, very exact about it. Actually, it's going to be right here. So this is the initial side, this is the terminal side, and this is the angle of 135 degrees, and it's positive angle, right, because it goes counterclockwise. Now the other one, negative 120. We're going to go in the other direction, in the negative direction. But in this case, instead of going 90 degrees like I did before, I'm not going to do that. I'm going to go negative 90 degrees, negative 180 degrees. And definitely, well, if this is the initial side again, the positive x-axis is always the initial side. Is worth worth noting that. Well, 190 degrees and then 30 more degrees. That should be somewhere here. All right, and that's our negative angle, goes in clockwise, negative 120 degrees. All right. So those are a couple of examples of locating angles. Now, well, when it comes to working with degrees, well, depending on certain applications, some applications may ask you to work in decimal form, and some other applications may ask to work this angle in degrees, minutes, and seconds. Well, so like we mentioned before, so this Cartesian plane is divided into 360 angles. Now, each angle can still be subdivided into minutes and seconds. So, for example, just like the clock, 1 minute is 1/60th of the degree, while a second is a tinier part of those minutes. In this case, 136 degrees. All right. So, well, an angle of, for example, let me give you an example. I don't know, maybe 15 degrees. 45 minutes and 17 seconds. The way we denote this is 15, the degree symbol, 45 minutes, the number 45, and we use one quotation mark for the minutes, and 17 seconds for the seconds. We use two quotation marks. All right. Now, how are we going to convert between degrees, minutes, and seconds to decimals? And how do we convert from decimals to degrees, minutes, and seconds? Well, the first one is really easy, is really short to do, but the second one might require a little bit more of a work. All right, so let's have a look at this. So when we are given an angle in degrees, minutes, and seconds, and we want to convert to decimal, so what we need to do in this case is to split these numbers as a sum. All right, the degrees, the minutes, and the second. We multiply the minutes by 1/60, and we multiply the seconds by 1/3 over 3600, because that's the part that they represent in our circle. All right, so and for the algorithm or the process to do the other reverse, well, we will see all these steps in action. In the meantime, let's do one simple example to convert 45 degrees, 10 minutes, and 15 seconds. Let's convert those into decimal form, and then round the answer to 4 decimal places. All right, so let's see. So 45 plus 10. I'm gonna leave some space here. Well, let me actually multiply this by 1/60 plus 15 over 3600. All right. And all we do here is simply put this in the calculator. Okay, all we do is put this in the calculator. Okay, where did I put my calculator? It should be right here. Okay, and I have already done this before, so all we do is type this in the calculator. 45 plus 10/60 plus 15/3600. 360, so 3600. And all we get when we evaluate this, we get 45.1708 because we want 4 decimal places. All right, so that's one example. Well, now let's do the reverse. So now we have an angle in decimals. We need to transform this into minutes, into degrees, minutes, and seconds. So what are we going to do? So let's go back and read the steps. So first of all, write the given angle as the sum of its integer part and its decimal part. So that is 12.87 equals to, in this case, this is going to be 12 degrees plus 0.87 degrees. All right, and we're going to split that into these two numbers. Number 2, multiply the decimal part by 60. That is, we do this to obtain the minutes. We should obtain an integer and most likely with decimal. So let's go ahead and do that. So in this case, what we do is, well, let me change the notation slightly first. So this is 12 degrees plus 0.87 of 1 degree. So this minutes, so this is 1 degree. Okay, and then I'm going to convert this 1 degree into, I'm going to represent it into seconds, or actually minutes. 12 plus 0.87 times 1 degree is equal to 60 minutes. And I'm going to multiply these two. So I'm going to multiply 0.87 times 60. And this is going to give me, so that's 12 degrees. 0.87 times 60, that's going to give me 52.2, and in this case, minutes. All right, so we got the minutes now. And in this case, we need to repeat the previous steps to obtain the seconds. So let's split this into the following sum. We split that into the following sum like as follows. 12 degrees plus 52 minutes plus 0.2 minutes. These two together gives me back these two. All right. Now, here is where we convert these minutes into seconds, and we do that by multiplying. Well, let me change the notation here. 12 degrees plus 52 minutes plus 0.2 of a minute. I'm gonna call this a minute. And then now I'm going to convert these minutes into seconds, because 12 degrees plus 52 minutes plus 0.2. Instead of 1 minute, because we want to convert this to seconds, I'm going to multiply this by 60 seconds. All right. I mean, we could have done we could have gone directly to multiply by 60 and then the remaining by 60. But the reason why I'm showing all the steps is so you can see the conversion between, in this case, between the degree and the minute, and then the minute into seconds. So you can see all further what's this called, all these further conversions. So now it's time to multiply 0.2 times 60. That's going to give me a 12. So 12 degrees plus 52 minutes and plus 12 seconds. But this is not the way we report as a final answer. In our final answer, we just get rid of the plus signs, and this is simply 12 degrees, 52 minutes, 12 seconds. All right, and this is final answer for this. You might wonder, well, can we do this using our graphing calculator? Of course, we can do that. Well, so let me do part B first. Let me convert these decimals into DMS. So the way we are going to do this is, let me clear this. I'm going to click. So the first thing we do is type the angle 12.87, and we're going to go to second and click the apps button where the angle is in blue. So you're going to get that. And then scroll down to number 4. Scroll down to number 4 where it says DMS. And in this case, just click enter and then click enter again. And that's how we get this using the calculator. Now the reverse is a little bit tedious to do because we will need to press many buttons. So first of all, I need to type the degrees. So the degrees, which is 45, I'm gonna go second and then apps again, angle, and the first is going to give me the degree symbol. Click enter, and that's the degree. Now I need to represent the minutes, the 10 minutes. So 10, type the number 10, go again to second, angle, and in this case go down to number 2 to type the minute symbol. Click enter, and then type the number 15 for the seconds, but the seconds are located somewhere else because in this case, well, okay, let me just show you second, angle. We don't have that double quotation mark. All right, so we need to quit, and in this case, the quotation mark for the second is right here. We can barely see. It's kind of hard to see. It's where the plus sign is. We have the mem in blue and this quotation marks in green. So what we're going to do, well, because this function is in green, I'm going to go and click alpha. Not here, hold on. Let me scroll down over here. So I'm going to click alpha, and then I'm going to click the plus sign. Doing it so it's going to type the second symbol for me, and let me click enter, and we should get the same answer, 45 and 17:03. All right, now let's move on to the next topic. Well, at this point we already learned how to work with different ways to express angles, degrees, minutes, and seconds, or simply decimals, and that's going to depend on the application that you use this couple of systems. All right, finding the length of an arc of a circle. Well, here is where we introduce another angle measurement system called radians. So radians are another way for measuring angles, and this is the typical measurement, the preferred measurement for calculus. But how do we find those radians? The radians are the ratio of the arc length to that of the radius. Well, let me draw a real quick picture here. So in this case, let me draw a circle, and there's the center. This is the angle somewhere here. All right, this is the radius of the circle, and this length right here, this circular length, this portion of circular length is called the arc length. And that arc length is formed by opening this, by making the opening of the two rays right here, and depending on the angle, right? And this is also called S, which is, and this is R, the radius, right? And by the way, this one doesn't have any units, because if we look at the units of the arc length, for example, let me for instance say that this is in centimeters, and the radius is also a length which is also in centimeters. Centimeters and centimeters, they cancel out, so that's why we don't have any units for radians. Now, how do we calculate that arc length? Well, for For this same circle of radius r, which is a central angle of a circle, and which is actually the vertex is in the center of the circle. And once we start opening the angle like this, once we do this, so that the angle that forms also forms some length, some curvy length, and it's given by this formula. All we do is multiply the radius times the angle, but this has to be in radians. Well, so let's look at one example. Find the length of the arc of a circle of radius 4 meters obtained by a central angle of 0.5 radians. So the formula, arc length equals radius times the angle, r, which is 4, times the angle in radians, which is 0.5, and we multiply these two numbers, and that's simply 4 times 0.5, that's a 2 meters, actually, because in this case it's the arc length. So the arc length has units. Okay, so now that we have another system of measuring degrees, we can further convert between degrees and radians. And well, in this case, I have pretty much if you will, the recipe to convert those angles, but it would be worth to explain where is this coming from. Well, all we do is to convert degrees to radians, just multiply by pi over 180, and to do the reverse, multiply by 180 and divide by pi. But let's explain where it's that coming from. Well, so if, for example, well, this is our initial side. This is essentially doing an entire rotation. That is, this means 360 degree angle, right? That's what a whole rotation is. Well, so let's see, if we use the formula from before, the arc length formula, that is S equals r theta. Well, we can combine this formula with the circumference formula. All right, with the circumference formula to find the perimeter of a circle. That's also known as the circumference, the perimeter of a circle, and it's given by 2 pi times the radius. So let's combine these together. What I'm going to do is I'm going to replace this s with that. All right. So what we get in this case is 2 pi radius times the radius theta and the angle. So in this case, we can just divide by the radius, right? So in algebra, when we cannot just do this, because what if r is 0? Then, well, we would be potentially dividing by 0. But in this case, we can safely divide by r, because the radius is never 0 for a circle. Okay. So what do we get? That 2 pi equals theta. Okay, or theta equals 2 pi. Now, this theta, this angle, is how many degrees? 360 degrees. So that means that one rotation, this 360 degrees, equals to 2 pi. All right. In other words, one revolution is 2 pi radians. This is what we wanted to show here real quick. Now, if we treat this as an equation, we can further simplify this, because both sides we can divide by 2, and that's going to give us that pi equals 180. Okay, 180 degrees, and from here, that's what the unit proportion is. So pi over 180 is basically 1 unit of half a revolution, and we can use this to, and this is where the pi over where the multiplication by pi over 180 or multiplication of 180 over pi comes from. Basically, well, if you have taken a chemistry class, it's like doing stoichiometry. You know, you multiply by one of the factors one way or the other depending on what you want to obtain. So in this case, it's the pi over 180 or 180 over pi. So let's do a couple of examples in which we convert we convert degrees to radians. So to convert degrees to radians, well, let me actually keep the page here. So we multiply by pi and divide by 180. Okay, so this is what I'm going to do first, because we want both the exact and decimal version. So when I multiply, okay, 60 over 180, that's 0.33. Okay, let's change to frac. That's 1/3. That's basically pi over 3. And approximately this is second pi over 3. That's 1.47. How many decimal? Two decimal places. 1.05. It works for negative as well. Again, the angle is 45 in the negative direction. Well, let's multiply by pi over 180. And in this case, well, let me divide 45 by 180. So right now, well, we are getting those values from scratch, but later on we're going to get used to this, and that's 0.25, which is, okay, math frac, that's 1/4. That's pi over 4. But keep in mind that this is negative. Okay, so let's multiply this times pi. How do we get to pi? Well, the pi, okay, I'm going to do this again, 1 over 4 times pi. The pi symbol is where the exponent notation is. So we go second and this to get pi, okay? 0.785, that's 0.79. So that's 0.79, which is actually negative. Well, in this case, 170 degrees multiplied by pi divided by 180. And, well, in this case, well, the numbers are not divisible, so that's simply 107 pi over 180. And approximately, this is, so 107 second pi over 180. And that's 1.867, 1.87 if we round to 2 decimal places. All right, so let's do the reverse. So for the reverse, which is convert these angles, these given radians, into degrees. So now we do the reverse, multiply by 180 degrees over pi. And in this case, well, the pi symbol goes away for this guy, and we get 180 over 6 and this is 30 degrees. In this case, well, there's no decimals at all. All right. And for part B, let's do the same, 180 degrees over pi. The pi symbol goes away, those cancel. And, well, we can multiply 3 times 180 and then divide by 4. Let's see what we get. 3 times pi, oh no pi, 3 times 180 and then divide by 4, and that's 135, but keep in mind that this is a negative angle. And then 3 radians. 3 radians, well, that's simply multiply by 180 and then divide by pi. Now 3 times 180, that's 180 over 180 times 3, that's 540 over pi, which approximately this one divided by pi, that's approximately 177, 88.7, that's 89 when we round to 2 decimal places. All right. Okay, what else can we do about these circles and radians? Well, finding the area of a sector of a circle. Well, suppose we have this this circle and we want to find the area, you know, we want to find this area of a sector. We use this formula: A equals 1/2 times the radius squared times the angle. All right, so in the angle, be sure that the angle is in radians. Okay, let's look at an example to show you how we go about this one. So find the area of the sector of a circle of radius 5 formed by an angle of 40 degrees. Round the answer to 2 decimal places. Well, let's start writing down the formula. A equals 1/2 r squared times theta. Alright, so if we put the numbers just like this, well, we can, that's fine. However, be careful when we multiply, when we put the angle part. Okay, so all I'm doing here is plugging in the radius r equals to 5 over here, which is right here, and theta is the 40 degrees. However, we cannot just simplify this right away. We need to convert this to radians. This angle has to be converted to radians. So I'm going to multiply by pi and divide by 180. Okay, so let me explain why. Okay, this has to be in radians, so we multiply that by pi over 180. So let's see. So I think in this case we're ready to just simplify. So 5 squared, that's 25, 1/2 times 25. And 40 over 180, that reduces, okay, let's cancel the zeros. 4 over 18, that's 2 over 9. 2 over 9. And that's a pi. All right, we'll leave that pi over there. And, well, actually we can still further simplify these twos, and we will be left with 25 pi over 9. That's the exact answer, and we need to further simplify this. So 25 times pi over 9. And that's going to give us 8.73, rounding to 2 decimal places. 73 feet squared. All right, that's because it's area. Another very common topic to discuss when we first introduce trigonometry is a little bit of circular motion. So find and relate the linear speed to that of a circular speed. Well, what we know from basic science, you know, so in this case, well, when an object moves around a circle at a constant speed, s is the distance traveled, and t is in the time t. And that's the linear speed. You know, that's basically distance over time. That's what we know from really basic science. And now, how can we turn this into circular motion? Because, you know, objects also move in a circular shapes, and that's what we we will in this case use a different term called angular speed. So the angular speed, which is actually denoted with the omega, with lowercase omega letter, okay, of an object is the angle swept out by, and we divide that by the time. So in this case is, so I suppose for example like a car moving in straight direction, either whatever the direction is, for right or left, well, like 5 meters per second, right? So that means in 1 second the car is moving, it's being displaced by 5 meters. But in circular motion, we don't do centimeters or meters, but rather degrees, or actually radians, right? In this case is the ratio of the number of radians per unit of time. So that's how we define this angular speed. And then we can further combine a linear speed with angular speed using this simple formula. But well, where is this formula coming from? It would be worth to look at this. Well, we know that the linear speed, let me actually, linear speed is distance over time. All right. But in this case, well, this distance is circular, you know, so circular distance. If you look at the picture for the problem we're about to solve, well, notice how this rock is moving in a circular direction. Well, so circular distance, what do we know? Where have we seen that this circular distance? Well, not too long ago. Actually, that's our arc length. Arc length is basically circular distance. All right. So I'm gonna substitute this S as r times theta over time. All right. And then, well, how can we simplify this? Well, if we look at this, the angle, the unit in radians, the ratio of the radians per unit of time is omega. So this is r times omega, and isn't it the same formula? Is way shorter to relate. All right, so a child, let's look at this word problem. A child is spinning a rock at the end of a 2-foot rope at a rate of 180 revolutions per minute. Find the linear speed of the rock. So let's see. The question is, what would be the speed of the rock if the rock was, for example, moving in a linear motion instead of a circular motion? So what's in a way the equivalent to it? All right, so let's write down the formula. Well, so they want us to find the linear speed, which is v, and it's given by the radius, which is 2 feet or 2 foot, and omega. But the omega, be very, very careful. 180 revolutions per minute. We cannot just multiply this to times 180. We need to convert this revolutions per minute into radians per minute. All right. So how are we going to start? So again, if you have taken like a chemistry class, this is like solving a stoichiometry problem or like unit conversion problem, if you will. So I'm going to start with the 180 revolutions per minute. Okay, so 180 revolutions per minute. So I need to convert these revolutions into radians. But what do we know? What do we know about this? Well, we know that these revolutions per minute we can convert. We know that this is 2 pi, that's one rotation, 2 pi radians is 1 revolution. All right, 1 revolution. And let's go back to where we got that, right? 2 pi radians is 1 revolution from page 4 of this handout. And that's how we are going to convert these units. All right. So let's cancel out the revolutions, and we are going to obtain radians per minute, which is what we wanted to use in this formula before plugging in anything. Okay, so 180 times 2, that's 360 pi radians per minute. All right. So now that we are ready to plug this in the formula, let me go back over here. The linear velocity will be the radius, which is 2 feet. Okay, 2 feet times 360 feet per minute. No, not feet per minute, radians per minute. All right. And in this case, well, just multiply this and we're gonna have 720, oh, that's a pi here, 720 pi, because, well, we can just keep the symbol, we can skip the radian symbol and just simply say that this is 720 feet, 720 pi feet per minute. All right. And if we can approximate this by simply multiplying the number 720 times pi, and that's roughly 2261.9. Let's actually round to the next integer, 2262 feet per minute. All right. And this is the end of this section. It's a good place to quit. I'll see you in the next video.